Okay, so we set up some background with a few papers about what extremes are in the Indian monsoon from the Goswami's book chapter from Tropical Extremes. We set up some scaling arguments for global precipitation and for precipitation extremes, short duration and large scale, and so on. Now we'll go through this paper just to conclude the discussions, just as an introduction to extremes. This is not really a course. So this paper is from the Wire, or Wires as it's called, Indian Summer Monsoon Extreme Events, Historical Changes and the Role of Anthropogenic Forcing by Dipti Singh, Subimal Ghosh, Matthew Roxy Cole and Sonali McDermid. They have their own take on how to organize it, and I will just go through them and add a few points to some of the points we already made, in fact. So this is the annual number of deaths associated with flooding events in India, and you can see that there are generally a varying number of deaths. In general, when you look at cyclone disaster management and floods in general, India has gotten better, especially some states have done much better than others, but then you have extreme events like cloudburst and landslides that happened in Uttarakhand in 2013, where you have a massive number of deaths because those are hard to predict in the first place, plus the combination or compound events where very heavy rainfall causes landslides, and then it's not a disaster management at that point. It's failed the zonal zoning laws, or construction, living on dangerous slopes, and so on and so forth. Nonetheless, we'll start with looking at the monsoon depressions or low pressure systems, which we already mentioned. We'll make some additional points, but first point out that the extremes over the South Asian monsoon region or the Indian subcontinent are also heavily related to land use and land cover type. So we'll make some points about urban flooding a little bit later on based on extreme events, which we already mentioned in terms of short duration events, which are very critical for understanding and predicting to manage flash floods, especially in paved areas. This is the percentage irrigated area over India, and the land use types here include barren land, built up and urban areas, croplands, fallow lands, and so on to water bodies. And there are multiple types of impacts. One is that the land use type itself, for example, soil moisture, urban heat island effects, and orography, etc., make a dynamical and thermodynamical difference and precipitation efficiency differences for creating extremes, and then the land use type can also make the impacts much more grave than natural landscapes, where you might have natural defenses like forests and so on, right? So here is land use and land cover map of India for 2005 based on multiple satellite remote sensing data and extensive ground truthing following the International Geosphere Biosphere Program classification scheme here. B is the percentage irrigated area in 2015 under Creative Commons source. Morris derived annual mean mid-visible aerosol optical depth. We will visit aerosols as well. Aerosols also will make varied differences to precipitation itself. For example, aerosols have direct impact where they scatter or absorb sunlight and affect energy balance, but they also have indirect effects where they can change cloud properties. They act as cloud condensation nuclei. They can change cloud brightness. They can change droplet size distribution, total amount of rain, and there is some evidence that they also affect extremes. But as we said, finding data to separate aerosol effect from all the other effects we've been looking at in terms of precipitation efficiency, vertical motion or dynamic effects, and humidity, saturation, vapor pressure with temperature, so thermodynamic effect is not so easy. Nonetheless, people use models, and we have already seen one example where the precipitation driver response model intercomparison showed how different types of aerosols and greenhouse gases can have different impacts on precipitation, duration, intensity, and frequency. So all these things are obviously very complicated. Coming back to the Indian monsoon more specifically, we already looked at this, and I mentioned the fact that a lot of the action during the summer months is in the eastern Indian Ocean, with the upwelling creating this region of lack of rainfall during the summer monsoon season. So here we have the monsoon intra-seasonal oscillations, heavy precipitation over the Bay of Bengal. You have the Western Ghats related precipitation, and the Himalayan foothill with the core monsoon zone in the middle. So you have the African highlands here, Himalayan foothills here, the Burmese mountains here. So you have this kind of a bucket that is formed. And as we said, the Indian Ocean is so warm that during the summer months there is still a marine ITCZ that remains, unlike in other places where the ITCZ tends to follow the sun. So why do we bring up the mesos again? Because we are going to look at these daily time scale extreme rainfall events which are associated with low pressure systems and depressions, which we mentioned as low pressure systems with wind speeds greater than 8.5 meter per second, and depressions greater than 8.5 to 16.5 meter per second. If you go above that, you become a tropical cyclone. So here is the composite rainfall anomaly for extreme wet spells and extreme dry spells, which is what we call the active and break periods. So composite precipitation anomalies from the July-August 1951 to 2011 mean for all extreme wet and dry spells in 1951 to 1980. Wet and dry spells are defined as events with rainfall anomalies over central India exceeding ±1 sigma for a minimum of 3 consecutive days. This is just the definition that's used. And we will see in a little bit that the character of this intrinsic time scale in the monsoon itself is changing. But right now we will see the monsoon low pressure systems aspect of this. Here we are looking at genesis in the red dots, and then their trajectory as the blue lines extending from the genesis point, and the blue dots, which are, or black dots, which are the termination. So this is looked at for the period of 1888 to 2003 by this very nice paper that looked at the complete phenology and processes, many processes of the low pressure systems. So they identified 1,520 low pressure systems totaling a 6,841 low pressure system days. So each one can last 3 to 6 days, and as we said, they contribute anywhere from 40 to 60 or more % of the mean seasonal rainfall. The other main point we had made was that the low pressure systems are very active during the active period that we just mentioned, and during the break period there are low pressure systems, but not very well organized and far and few between. So when we want to see extremes, these are the ones that can bring very heavy rainfall, including almost 70 millimeter per hour rain rates. Can be a couple of 100 millimeters per day in some cases. So obviously they are associated with extreme daily timescale precipitation events. This is from the same paper by Krishnamurthy and Ajay Mohan, which looked at the OLR LPS composite during the outgoing long wave radiation for low pressure system composites, and this is the non-LPS composite. And you can see this large scale dynamic pattern that's always there, going from the northwest tropical Pacific all the way across India into the northwest. And you also have this north-south pattern corresponding to the precipitation over India, over the tropical region being out of phase typically with the active phase here, and there is a east-west pattern with the northeast India typically being out of phase with core monsoon zone. So we have mentioned already the 10 to 20 day systems, which tend to come towards the northwest, and the 20 to 90 day systems or 20 to 60 day systems which go northeastward. Right? So this is the non-LPS composite, where you have OLR is high, means you have basically no convective systems, right? Tall clouds convection, tall clouds low temperature produces low OLR, so negative OLR here as a deviation from the seasonal mean, or filtered in some way at 20 to 60 days, gives us convective phase and dry phase, active period and break period. So when we want to think about these extremes, we have to think about the warming that's happening over the ocean, over land, over aerosols, role of the warming over here, role of the MJOs sometimes, the heating on the Iranian plateau, Tibetan plateau, the trends in them, the aerosol loading here can affect the circulation over here, and all these factors play into how the extremes, including land use, so soil moisture, irrigation, agriculture, urbanization, all these things are going to affect how extreme events are going to be produced with the low pressure systems coming over, including orographic effects here, the central Ghats and the eastern ranges, and so on and so forth. I'm mentioning all these because, again, we lack complete understanding, as we have seen already, but data is always an issue as well, as we mentioned in the case of people debating whether there is a trend in these monsoon depressions or not. So some argue there is a trend, some argue that there is an increasing trend in the synoptic systems at 3 to 10 days, but the low frequency systems from 10 to 60 days are decreasing, and some argue that in fact there is no trend when you properly track the low pressure systems. Okay, to look at what other external factors can affect LPSs, we have already mentioned El Nino and La Nina. El Ninos tend to produce droughts over India, and La Ninas tend to produce floods, but only about 50% of these are explained by El Nino and La Nina. So if you just look at the composites of low pressure systems for all the flood years and drought years in the time period considered, there were 187 LPSs in the flood years and 251 LPSs during the drought year, and 841 LPS days here and 1104 LPS days here. What does this mean? Obviously, the monsoon has a seasonal mean and a monsoon trough that is producing a seasonally persistent pattern. And then you have convective systems and these LPSs which are contributing. So how the wet years and dry years are determined in a seasonal mean doesn't just depend on LPSs. That's what this is saying. So in other words, whether to understand the impact of LPSs on wet and dry years, or to understand external forcings like El Nino and La Nina on producing LPSs, as well as floods and droughts, have to be understood to better understand the extremes and better able to predict them as well. So looking then at El Nino, you have 1060 LPSTs, low pressure system days, whereas La Nina only slightly higher with 1156 low pressure system days, which means that there are other processes like the Walker cell, the local Hadley cell, changes in the southwesterly jet, and so on, that contribute to the monsoon variability on El Nino and La Nina timescales. Consistent with that, we see that in fact there is a very little correlation between the El Nino index Nino 3.4 and the low pressure system days. Okay, so low pressure systems are essentially associated with the monsoon intra-seasonal oscillations which are coming north from the tropics. They are bringing a lot of rain and daily timescale extreme events over at least the core monsoon zone, but exactly what controls their low frequency variability is not entirely obvious. Okay, that's what we have to keep in mind. But obviously the understanding continues to be improved, and the extended range forecasts also continue to be improved. So if active days and break days can be predicted, then we know already, as we said before, the chances of LPSs and daily timescale extreme events is higher in the active period. So already the opportunity for better anticipating extreme events at daily timescale goes up with that kind of predictability. So we'll then move on to the next timescale of intense rainfall and look at some mid-latitude interactions in the next podcast. Okay.